Are we going to wait for Gordana? Is she here? No, she's not.
Where she is, but I'd say get started. I think.
Okay.
She'll be here.
Should I go ahead and screen share it? I'm not sure if I have the privileges.
I'm not the host, Dave.
Okay.
Oh yeah, you should have permission to share. I think. Yeah.
Well, I'll just pull up the beginning in case.
Yeah, that's good.
So, should we start? Kyle, are you ready?
Absolutely.
So our speaker today is Kyle Hayden from Columbia, and he's going to tell us about Knotty algebraic curves. Thanks.
Yeah. Thank you, Malcolm, for the introduction. And thank you for the invitation, and for you guys for being here. It's great to see some faces I recognize, and some ones I haven't actually had a chance to always meet in person. So it'd be nice to get to chat for a minute at the end. Yeah, so what I want to talk to you about today are, well, I'll call some Knotty algebraic curves. There's a bit of a sneak preview of the picture on the beginning. Two things before I forget. I'll try to keep an eye on the chat, but if you have questions, please just jump in. I'll also try to pause, but do feel free to interrupt me. And secondly, the exact form of these slides might not be on my website, but if not, if you go to my website, which I could put in the link to, a version of a very similar set of slides are available. Let's see. Okay, so let me just share that in the, oh, actually, okay, well, maybe I'll share it at the end, just for the sake of time. Okay, great. All right, so to start off, I want to sort of set the stage by talking about the fact that in dimension 4, we start to see some differences between categories of topological spaces that don't exist in lower dimensions. So typically we'd be thinking about the smooth category, topological category, and piecewise linear categories. And sort of in some sense, the earliest result in this direction is that, while all 1, 2, and 3 manifolds sort of have emit the structure of topological manifolds, also emit smooth structures and piecewise linear structures and unique structures in each of these cases. There are 4 manifolds, which are topological manifolds, closed, compact, that don't emit any smooth or PL structure. And so the easiest examples of these you can cook up would be the E8 manifold. And it exists sort of by work of Friedman. It can't be smoothable by work of Rockleen on the signature or on the intersection form of smooth 4 manifolds. So but maybe, there was a talk that Michael Friedman gave relatively recently where I don't know exactly how you quantify the statement, but in some sense, at least up to a certain level of complexity, there are like more non-smoothable topological 4 manifolds than there are smoothable ones. In fact, there's tons of them. So maybe we want to try to restrict to thinking about, well, what happens if I think about smooth objects themselves? If I tighten the screws a little bit and try to rein in the categories, well, sort of both as a shameless plug, but also because it sort of came up during a lunch. I want to mention this, the relatively recent result. If you now sort of fix your ambient world to be smooth, so that's nice to work in, what if you just let the sub-objects be a bit hairier? So some work, joint work with Lisa Picarella from last year, reproduced topologically locally flat surfaces. I'll say what those are in a moment. In 4 manifolds that can't be approximated by smooth or PL embeddings. So what's a topologically locally flat surface? These are the types of topological surfaces we like to think of when we're thinking about Friedman's work. The point is that these are, if you thought about in general, what's a submanifold going to have? If we look at a chart nearby, if it's a surface, it'll look like R2 inside of R4. If it's a smooth surface, let's say it would be diffeomorphic locally to R2 cross 0 inside of R4. When we say these are locally flat, we're going to mean that they have a topological chart everywhere nearby, so they're locally homeomorphic to R4 comma R2 cross 0. And so last year we showed that, in fact, not only do surfaces topologically flat surfaces exist that can't be approximated by smooth or PL embeddings. They're everywhere. So if you take your favorite smooth embedding of the 2-sphere into R4, you can jiggle it just a little bit such that you can't get arbitrarily close to it again with smooth or even piecewise linear embeddings. And so when you think about piecewise linear, you can essentially think about it as being smooth, except at finitely many cone points where you see sort of regions like are being modeled over here, where you have the cone on some knot. So even if you allow that type of pathology, you still can't approximate these topological surfaces.
So what does approximate mean exactly?
Yeah, great question. So there's several different equivalent ways you could make this most precise. I think that the cleanest to state is to say that if we think about the space of maps from, let's say, the 2-sphere into R4 with the compact open topology, so the usual topology we put on that as a space of maps, I could think about, I've got different pieces of it. I got spaces that are embeddings. I've got, places that are not embedding. There's immersions in it, everything. What this is saying is if you look at the set of smooth embeddings, that's a subset of the set of topological embeddings. And the point is that basically you can take what's the right word? So you can take a topological embedding in that space, which you can't even sort of get close to it through. You can't get a sequence of embeddings converging to it that are smooth or piecewise linear.
I think the question was, what is close? Can you do it in Gromov-Hausdorff topology? Kind of just measure the distance? Since you're in R2, can you just use the metric distance? From a point on one manifold, subvariety to the closest point on another.
Yeah, so if I understand the question, that's going to induce the same coarse topology on the mapping space, I think. Right? I think that'll give you the same. If you have, I think, spaces of manifolds, I believe that the different choices of metrics on that underlying space, they'll give you the same topology as long as they satisfy some very basic, reasonable assumptions. And I think that if you just take the actual, that's what the C0 norm basically, I think that's going to be the same space. So the point is, right, you can choose an arbitrarily small neighborhood of a nice little 2-sphere, jiggle it a little bit, make it a little fuzzy, and then you can't get back into this little neighborhood with smooth or even piecewise linear embeddings.
Yeah, so I guess what was confusing me was the approximation means a sequence approaching it. Whereas
that's right.
I was thinking, I take this S2, it's smooth, I jiggle it. Why isn't that, why isn't it already an approximation?
Right, yeah, and exactly.
It's a sequence, that's what it was.
Exactly, and so it's sort of still, this jiggle thing is somehow insulated from the rest of it. And the other point is that it's not just that you can find some awkward topological surface which is far away from any smooth ones. These can get as close as you want to a nice embedding. So they creep up on you all the time, yet as soon as you try to move towards them, you're blocked from getting too close. So to any individual one, yeah. Okay, and so in fact, this holds for any smooth embedding of a surface into any 4 manifold. And now, this isn't by any means so that the main point of talk. I sort of wanted to indicate, as we start to sort of tighten the screws and try to improve the regularity and the rigidity of our objects, what happens? So here you're seeing, if you restrict yourself to work with smooth 4 manifolds, you can find these pathological sub-objects. Okay, so let's keep tightening. And now what if we just want to consider only smooth objects? So there's lots of sort of exotic phenomena, that's what this is usually called in 4 dimensions, that falls under the heading of sort of topologically the same but smoothly different. And so these are the sort of the big exciting areas of active research for the subtleties of smooth topology in dimension 4. Probably the biggest main result to throw out is that you can look at if different smooth structures on an underlying 4 manifold. There are four manifolds which are homeomorphic to R4 but not diffeomorphic to R4, and they're smoothable. Our work of Donaldson and Freeman. I'll jump back to Zach's question in a moment. So just to make a contrast, if you're in any other dimension other than 4, if you're homeomorphic to Rn, then you're also diffeomorphic to Rn. So in other dimensions, there's a unique smooth structure on Euclidean space. Okay? So it really singles out dimension 4 there. Another type of phenomenon you can look for is exotic surfaces. So for example, there are smooth closed surfaces in CP2, complex projective plane, such that they're homeomorphic as pairs. So there's ambient homeomorphism, in fact, a homeomorphism which is isotopic to the identity through homomorphisms, but there's no diffeomorphism of the pairs. So they're topologically the same, but smoothly different. First results in CP2 in particular, I believe, are due to fashion. Also in general, construction of exotic surfaces, much of the work was done by Fentuschel and Stern. And I just want to point out that you can actually take one of your surfaces to be the standard nice complex surface you would look at in CP2, so a degree D curve. Okay, and you can find another copy which is topologically the same, but not the same through diffeomorphisms. Okay, and then a third sort of pillar of exotic phenomena in dimension 4 are automorphisms, which are exotic. So what do you mean by that? You have a single four manifold, single smooth four manifold, and two different self-diffeomorphisms, such that they're isotopic through homomorphisms, but not diffeomorphisms. Okay.
Sorry.
Yeah. So yeah.
Is there something wrong in that blue line? It's not homogeneous, you know.
Oh, did I not write that down right? I wrote it down without really thinking.
Kind of doesn't make sense. But...
Wait, what do I want for it to be homogeneous? For it to be
U1 equals 0.
Oh, wait, but that's I'm sorry.
4 equals epsilon times something.
Yeah, I'm sorry. The epsilon should be what? It should be in the factored into the
Z to the D.
Yeah.
Into each of the variables. Sorry.
Z to the D, maybe epsilon Z to the D.
Yeah. Okay. Sorry. I'm live. I'm not gonna be able to say it, but you're right. Yeah. All I mean is what you think of as the standardized complex pairs in CP2. So take any, in particular, you could take any polynomial and homogenize it, and then the only reason we have a shift is to make sure it's smooth because we want it to be non-singular. Okay. So right. Sorry. So yeah, I just jotted down blue without really thinking, but I just mean sort of standard surface. Right. And then Zach's question asked, why do cones on knots show up versus cones on a point? Versus cones on a point. Yeah, today's point, a cone on a point is an interval. Right. The point is that we want to get something which is two-dimensional. And so if we're thinking of the 4-ball locally as the cone on S3, if we have some knot in S3, you take its cone, you get a singular disk. So, okay.
Kyle, in that exotic surface example, are CP2 minus sigma and CP2 minus sigma prime are diffeomorphic?
Let me think. I don't think so. But so yeah, it's just I believe for all degree D except maybe 1 and 2, I believe.
Yeah, I don't think they're going to be diffeomorphic because they're not going to have diffeomorphic double branch covers. That's how you distinguish them smoothly.
Right. Yeah. So
I see. Okay.
Yeah. The one subtlety is that there are situations where, and I'll mention this in a moment, there are situations where the double branch covers of some exotic surfaces can be the same. And I believe also the exteriors, depending on how you cook them up using rim surgery. But yeah, for the standard examples, like Peter said, I believe their complements should be different too.
I see.
Yeah. So exotic surfaces will be where we're headed mainly next. But yeah, any other questions sort of on this backdrop? Okay, D at least 3. Great, thanks. Yeah. So for degree 1 and 2, those would be represented by spheres, and we don't have any exotic spheres yet known in CP2. Great. So what I want to compare to now is, as we keep sort of tightening screws and adding more regularity and perhaps some geometry, some of this exotic behavior starts to go away. Oh, sorry. So I meant to say this last one, an example of an exotic automorphism is a Dane twist on the separating S3 and connect some of K3 surfaces. But since that's sort of just a side accessory I'm throwing out, I won't spend any time on that. So what happens when you start to put some geometry in the picture? And in this situation, we start to see some of the rigidity evaporate. So particularly striking example is if I have a four manifold which is complex and has no second homology, and its boundary is the three sphere, it's done in such a way that the boundary is holomorphically convex, then this four manifold is going to be diffeomorphic to the four ball. Okay. So what this is what I'm saying is that once we start to really put some strong geometry on it, we start to lose some of the flexibility we might have seen before. Getting to the cases of surfaces, if we're looking at, in particular, sufficiently nice types of complex four manifolds, they're known as Kähler surfaces. So these are nice, sort of complex symplectic four manifolds. They have no, the first byte number is 0. Then any two smooth complex curves that are homologous are in fact isotopic smoothly, and not only smoothly, but through complex curves. So this is saying that once you restrict your attention to smooth complex curves in nice complex surfaces, in fact, homology determines isotopy. So you get a real collapse in terms of the rigidity behavior. So for example, this applies in CP2. And a broader conjecture, for thinking broadly about geometry, the symplectic isotopy conjecture predicts that any two symplectic surfaces in CP2 of the same degree are isotopic. And so this is known for up to degree 17, like work of Gromov and very low degrees, some others, and then sort of steady that are due to Siebert and Tien. And the final sort of example I want to mention is you have an algebraic curve in just the complex in C2, complex Euclidean space, then as long as it satisfies a regularity condition, or it's regular at infinity, I can say what that means, but it's just a regularity condition on the polynomial, on the fiber, then in fact that entire surface sitting in C2 is determined up to isotopy by the link that you get by intersecting it with some very large radius sphere. So in that case, again, you sort of see that the entire isotopy, isotopy class of the surface is constrained by some lower dimensional information, in this case, the link at infinity. Okay, so regular at infinity roughly means that nearby fibers look the same outside of a compact set. So it's not quite vibration, but there's just some sort of homogeneity condition with nearby fibers. Okay, so this is all just to give examples of ways in which the rigidity that you see in general collapses once you add enough geometry. Okay. So yes, any questions on that sort of the second part of this backdrop of motivation? Okay. All right, so what I'm particularly interested in is how things break down at this sort of this phase transition between the more rigid geometric setting and the looser sort of arbitrary smooth setting. And there are a lot of reasons to think about this. I mean, one reason being that oftentimes, especially in four manifold topology, a lot of the simplest objects and spaces you want to look at naturally are complex. For example, a lot of the basic four manifolds like CP2 or K3 or S2 times S2, these all admit these nice geometric structures. And so if you want to understand the sort of emergence of exotic phenomena, and you want to understand it in the simplest possible cases, you need to be looking at oftentimes some complex settings. Okay. And the perspective that I like to use on this type of problem is to try to investigate it using structures that are themselves sort of half topological and half geometric. Things like braids or open books or Lefschetz vibrations on four manifolds. And so these are sort of innately topological constructions, or I mean, barely smooth, but they can capture geometry through extra data. So in particular, here you might capture some kind of geometry through conditions on the monodromy of an open book or a Lefschetz vibration. Things like restricting to monodromy that's product of positive Dane twists, or Braid, which is sort of based on positive Artin generators. And that'll somehow confer some geometric rigidity or sort of read that back. Okay. And so in particular, what's the setting we're looking at today? It's looking at the case of exotic surfaces. So clarifying the definition from before, two smooth surfaces, sigma and sigma prime and X, are exotically knotted if they're isotopic under ambient homeomorphisms, but not under any ambient diffeomorphisms. Okay. So topologically the same, but smoothly different. And sort of have in mind as a major motivating question here, it's an open question whether or not R4 contains exotically knotted closed orientable surfaces. So it's known in the non-orientable case, there are sort of large, or not large, I mean up to, I think, sort of non-orientable genus 6, exotically knotted non-orientable surfaces, but unknown in the orientable case. And the setting that we're going to try to think about today in particular is a relative version of properly embedded surfaces in the four-ball. So I'll pause for a moment in case there are any questions before I state the main theorem.
So just to be clear, so the Fintuschel-Stern examples from before were exotically knotted in CP2, right? Yeah, so I think that those, I can't remember the exact, maybe Peter or somebody else remembers the exact chronology, but yeah, the examples in CP2 are due to either Fintuschel or Fintuschel and Stern sort of work related, but those are exotically knotted because, right, so there's an ambiently homeomorphic, but in fact, you can promote it to the homeomorphism to be isotopic to the identity topologically. Yeah, great. Okay, so in this relative setting, the first main result I want to mention, talk about today is that we're going to look at pairs of smooth, properly embedded disks in the four-ball that are isotopic under ambient homeomorphisms, but not under any ambient diffeomorphisms. And in fact, these disks are going to arise as intersections of the unit four-ball with algebraic curves in C2. Okay. But we can also, so the construction is explicit enough to sort of draw these things by hand. And that's what we were seeing here in the back on the title slide. So here we have two different pictures of what you call ribbon immersed disks in 3-space. And you can see sort of two different sides to each of them. There's a dark gray side and a light gray side. And we see some places where it twists over. And the key point is that any place where the surface is self-intersecting, it happens with sort of a narrow band passing through the face of some larger disk-like sheet. So the point is that intersections like that can be eliminated by pushing them down into the four-ball, sort of kind of like lifting up an overpass so that two roads can cross without crashing into each other. Okay. And the other thing is that you'll notice that the boundaries of these disks are virtually identical. They're not spot on the nose identical. To make it easier to draw, I've taken this crossing down here and slid it up to sit over here in this picture on the left. But other than that small fib to make the disks easier to draw, you can tell that these disks are bounded by the same knot. But visually, they're not the same disk. And in fact, these are examples of these exotically knotted surfaces in the four-ball. So a couple remarks. So these rise to the first examples of exotic complex curves. They're both in the four-ball, but also sort of you can enlarge these into other Stein surfaces and nice complex spaces. There are infinitely many pairs like this, and you can extend to sort of arbitrarily finitely many. But didn't you say the ones in CP2 were exotic complex curves, or only one of them was exotic? Oh,
exactly. Sorry, only one of them. Exactly.
I see.
Yeah. And I'll make a remark about that because that's sort of an interesting fundamental problem about how much can you put on both surfaces in consideration versus one. Right. So yes, you can have there's infinitely many pairs like this. You can extend to finite families, and you can also easily cook up higher genus examples from the lower genus examples.
Kyle.
Yeah.
Okay. So what happened if you just connected some to closed surface with these two copies? Are they still exotic?
I
I don't know about a closed surface. If you take, for example, like one kind of silly way to increase the genus is to take like the standard Seifert surface for a torus knot and connect some, boundary connect some that to these disks. Those will remain exotic. I don't know about if you tube on a closed surface.
I see.
Yeah, I'm not sure about that. It's a good question. Yeah.
What is the smallest genus?
So these are examples of genus 0. So right, yeah. So in that sense, they're minimal. Right. What you would really like to have is closed genus 0 as well, but that's very much open.
And Kyle, so do these have so their double range covers are homeomorphic?
That's right. The double range covers are going to be homeomorphic, but they'll be non-diffeomorphic.
I'm not sure what you said. So these are intersections with some algebraic curves. So
right.
That algebraic curve has a genus, geometric genus. So,
oh, I see. Okay, sorry. So you should. So this algebraic curve, these algebraic curves. So they're sitting inside C2, just inside the unit 4 ball. We see them intersect in these genus 0 subsurfaces. But I don't know globally what the genus is. Yeah, so it specifically will not be genus 0 though. That I can guarantee. You'll pick up some topology outside the unit 4 ball. Yeah, it's a good question. Great. So you can also embed these into closed surfaces inside larger four manifolds, including closed four manifolds. And you get some new sort of phenomena. You can cap these out to get some close exotic symplectic surfaces, including first symplectic exotic two spheres and exotic symplectic surfaces of non-zero self-intersection. And then the final point I want to make about these, before I actually talk about the construction, is the same time earlier this year, Andres Juhas, Maggie Miller, and Ian Zemke produced families of exotic surfaces of positive genus in the 4 ball. They actually produce infinite families because they use a construction which is better suited to infinite collections. Though their construction also requires positive genus. And their proof is really fascinating. It uses the TQFT structure on knot floor homology to distinguish the surfaces. And it's a very nice application of that. But it's interesting that their abstraction can't detect the types of examples that I'm producing. And I don't say that as oh boy, look at these examples, they're cool because of that. But what it means is that there's some sort of fundamentally different sources of what's leading to the exotic behavior here. Basically, the problem is that, or the difference is that their abstraction does not see the difference between complex curves, basically because of the nature of the types of cobordism maps those induce on knot floor homology. So the source of the exotic nature of these surfaces versus theirs are fundamentally different. But in particular, they won't be able to produce pairs of exotic complex curves or symplectic surfaces. Okay. So any other questions before I talk about the ideas that go into the proof? Okay. Okay, so just let's see what I have on the next slide. Yeah, okay. So as I mentioned sort of before during lunch, this is going to be a bit of a choose your own ending kind of talk. So the plan is that I'm going to very briefly, cartoonishly mention what some of the earlier constructions of exotic surfaces are. And then I'm going to describe just sort of somewhat bare bones the idea of what goes into these surfaces. And then have a few different directions I go in, depending on where the construction came from, or sort of more generally how to think about smooth surfaces versus complex curves. So just to start out though, let's just do a quick recap of the previous work on exotic surfaces. So the definition from above, surfaces are exotically knotted if they're isotopic under ambient homeomorphisms, but not diffeomorphisms. And so for the most part, the previous examples of exotically knotted surfaces are positive genus surfaces that arise from variants of an operation known as rim surgery due to Van Tuchel and Stern. And roughly speaking, the idea is that if you have some surface of positive genus inside some four manifold, you choose a loop in your surface that's essential. And now, if you think about a neighborhood of that loop, that was an S1 and it's inside of a four manifold, so it's an S1 times B3. But you've got this little annulus neighborhood of your loop inside the surface. And so above every point in your loop, you have like an interval fiber from your annulus neighborhood. And roughly speaking, what you're going to do is just choose some other knot. Here I've chosen a trefoil. And you're going to tie that into each of those interval fibers lying over the S1. So this is a bit of a cartoonish depiction of that. But this is sort of the only level of detail that we'll need for that. And the point is that under suitable conditions, like if the initial surface is, for example, symplectic, satisfies certain self-intersection conditions, you can guarantee that the resulting rim surged surface will be smoothly distinct from the initial one. Okay. It looks like my connection might be. Okay. Looks like my connection might be a little rough. I'm not sure if it's back yet.
You sound okay to me, so just keep plowing ahead.
Okay, cool. All right, so I'm getting some strange messages on my end, but I'll keep going. All right, so there is also a construction for genus 0, which is not showing up on my screen. But there's essentially one previous construction for exotically knotted two spheres studied in several people. But the basic idea is that it applies to four manifolds that have been connect-summed with some other standard piece that has in of itself some interesting two spheres in it. So the basic idea, well, maybe for the sake of time, I'll come back to that at the end if people have questions, but the basic idea is to look at these natural two spheres that lie inside these standard pieces that are connect-summed on. And so in particular, they don't have exotic spheres in irreducible four manifolds here. Okay. All right, so getting towards the construction of the disk that I was talking about, we're going to sort of present it in terms of Braid factorizations. Now, this isn't the same way the construction is presented in the version of the paper that's online right now. This is sort of something that is a nice alternative perspective that I've been trying to flesh out. But the underlying construction itself is inspired by Cork twisting, and I'll explain that if there's time. But for now, I'll present the idea in terms of Braid factorizations. So the starting point is a definition of Lee-Rudolph, which considers a special type of braid known as a quasi-positive braid. So a braid's quasi-positive if it's a product of conjugates of the standard positive generators in the braid group. So braid would be positive if it was a product of just the positive generators. And here it's product of conjugates of the positive generators. Okay. So what do these look like? Here's an example. This is a product of 4 terms. Each one is some central positive term that's been conjugated. And what you see, the sort of visually, the effect is that you see these bands in the braid words. And so when you close this up, you get some knot or link. And here's a second example. In the second example, this is what's called a strongly quasi-positive braid. I'm not going to define it precisely because it's not essential, but the point is up here, these bands went underneath some strands at different times. In a strongly quasi-positive braid, the twists always run in front of all the other strands. Okay? So that's sort of a constraint on what you're conjugating by. But the nice thing is that in the strongly quasi-positive setting, you can even see here, there's sort of this Seifert surface that's suggested, which has sort of white sort of upper sides and darker gray undersides. And so you just get a stack of discs, one for each strand in the braid, and then one band for each conjugated term. But there's actually no reason why we can't consider a similar surface when it's not strongly quasi-positive. So up at the top here, we see some, going back to that first quasi-positive braid, you can build up a similar surface, but now it'll have ribbon intersections. Even if the braid was not strongly quasi-positive, it was just an arbitrary quasi-positive braid. So for each quasi-positive factorization, we get some sort of ribbon immersed braided surface. And now what Rudolph showed is that if you have any knot, you can use these types of surfaces to cook up a smooth algebraic curve in C2, which intersects the unit 3 sphere in your knot, or at least in a knot isotopic to your knot. Okay. And in fact, he proved something stronger, which is that you can arrange the curve so that its intersection with the four-ball is isotopic to this positively braided surface that you get associated to the quasi-positive braid word. Okay. And so the part of why this construction is so useful is that it's relatively easy to control the topology of these braided surfaces. And then Rudolph's theorem promotes them to actual pieces of complex curves. So you get fine control of topology, yet you also get this sort of amazing, really rigid geometry of them being realized as pieces of complex curves. Okay. So this is going to be the toolkit that we need to construct our surfaces. So any questions about quasi-positive braids or the factorizations or the surfaces?
So it depends on the factorization. Probably that's going to be the point, right?
That's exactly going to be the point. The factorization, since it composes the surface.
Right. But then just about Rudolph's theorem, I mean, in principle, if you had the factorization, could one write down the polynomial, or is it more around?
Yeah, there's not quite. There's a line, I forget exactly what the line is, but there's a good line about it in one of his papers where he says that, I can't remember if he says that the proof is more or less constructive, but then elaborates that basically that the more or less, the problem is that you can build your surface and get something which looks like a polynomial for it in a funky looking bidisk. So it'd be some weird squiggly circle in the plane, and then you cross that with C2. But you really want the four ball, and so then you appeal to the Riemann mapping theorem and carry that weird funky disk onto the actual unit disk. And that's where you'll lose the explicit control. Yeah. Great. Okay. So as Dave mentioned, the fact that it depends on the factorization is exactly what's going to matter here. So different factorizations of the braid can give rise to different surfaces. This was first noticed by Rudolph, and he sort of gave some pairs of three braids with different pairs of three braids which were isotopic as braids, but the factorizations were distinct. And if you look at the surfaces associated to them, the surfaces are not even, I believe in that case, they're not even homeomorphic. You can use this to cook up, that is, the surfaces, I think one is connected and one's not connected, or at least you can take his examples and cook such surfaces up from them. And his original pairs of braids like this, they showed up again and again in different contexts, sort of a useful construction. But ultimately, the surfaces that you get are never even topologically the same. For example, those older factorizations, the branch covers have different intersection forms. So the name of the game here is to find some particularly subtle examples where the surfaces that you get are going to be topologically the same. And so that's what's going to give rise to this theorem, just restating it here from before. We'll get properly embedded disks. They're going to be positively braided surfaces, and so they're going to be isotopic to pieces of algebraic curves. And we'll show that they're topologically, but not smoothly the same. Okay. And I don't know that it's going to mean much to you, but if if you explicit braid words are your thing, here are two particular examples. These are both in the 5-stranded braid group, and you'll see that they have the same number of terms. Each have 4 terms in them, but evidently they're not the exact same factorization. Okay. The one thing I want to highlight about these is that they both start off with the sigma 2, and that's in some sense going to be the tip off that we're going to use for how to compare these things later on. So in one case, the first sigma 2 was used to conjugate a different term, whereas in the second word, morally, it ends up being that same sigma 2, but we've turned it into its own generator. And so I say that only as sort of foreshadowing how we're going to distinguish these surfaces. Okay. All right, so just repeating the difference. So where do these disks in particular that I'm drawing down here come from? These come from some larger braid word that contains those 2 braid words, beta naught and beta naught prime, and we swap out just the sort of sub-factorization. That's connecting the dots there. So what I want to do now is actually explain how we distinguish these surfaces, or how we show that how do we show that they're exotic surfaces? There's 2 steps. We need to show that they're topologically the same and show that they're smoothly different. We're already done showing that they're algebraic because they came from this construction, which by Rudolph's work already furnishes complex curves for us. Okay. So how do we show that they're topologically isotopic? Here we're going to appeal to the recent theorem of Anthony Conway and Mark Powell, sort of building on Friedman's machinery. So it says that any 2 pair of smooth disks with the same boundary in the 4-ball and whose fundamental groups that are exterior are infinite cyclic are going to be isotopic through homeomorphisms of the 4-ball that fix the boundary. Okay. So our braids, they were different factorizations, but they were the same underlying braid. And so they have the same boundary as knots. And you can calculate the fundamental group of the exterior in multiple different ways. For one thing, there's an algorithm for reading off the fundamental group of the complement of a braided surface from the braid word. That's one approach. Or you can just explicitly build up a handle diagram for the disk exteriors, and that'll give you a presentation for the fundamental group as well. So one way or another, yeah.
Is this criteria equivalent to Alexander polynomial 1?
It's not. Well, it depends what you mean. The underlying machinery is, but for example, these will not actually have Alexander polynomial 1.
Okay.
Yeah, so some of the examples will have Alexander polynomial 1, but right, this is using sort of the disk theorem machinery.
So I have a question about the
yeah.
So the calculating pi 1 is z. Is that? I mean, I'm not doubting you, but that there are famous examples of exotic 4 manifolds where people got stuck because actually they couldn't. They thought they could compute pi 1 of z, but they couldn't.
Yeah.
It's as simple. So are these kind of like easy computations, or are they incredibly?
Yeah, they're incredibly easy actually. That's the nice thing about this setting, because you're not doing any kind of complicated surgery type thing where you need to identify. Really, you're not carefully studying the change in some fundamental group. The presentation is quite easy to extract. Yeah, it's a good question. And one that I thankfully not face. Yeah. Okay, so that's what shows that they're topologically the same. And this is really using Friedman's work via the Conway-Powell result as a black box. But it's an easy to use black box in this case. Okay. So now we know that they're topologically the same. We know that they're complex curves. And so we need to show that they're not smoothly isotopic. And the strategy is going to be to study, sort of as we talked before, there's a couple ways to think about it, but we'll think about it first as think about the exteriors of the disks. So what we're going to do is we'll call the common boundary K. So that's the not drawn in the top. And what we're going to do is we're going to find a loop in the complement of K. So it doesn't hit K. It'll be this red loop gamma. And we're going to show that it bounds a disk in the complement of one of the larger disks, but not in the complement of the other. So we're sort of reframing a sliceless problem into the disk exteriors. And so how do we actually sort of study whether or not this loop bounds a disk? Well, but before I get there, I just want to mention why this loop. Where did this come from? If you go back to the original Braid words, I mentioned this sigma 2 that's differing between them. This loop gamma is exactly the loop which encircles the crossing in that sigma 2 generator. And so since that sigma 2 is somehow an obvious difference between the two Braid factorizations, that was sort of naturally why I went and looked for that loop. And why does it bound a disk in a complement of one of the larger disks? Well, if we look over down here on the right, if we take the red disk bounded by gamma, it's just going to have a simple ribbon intersection with the larger gray disk. So when I push things down into the 4-ball, I can clear that ribbon intersection. In particular, if I drop down past the index 1 critical point, the C's gets parted, and I can really actually plug up that gamma with a disk. On the other hand, if we look at it in the complement of D, we said there's sort of these clasp intersections between the gray disk and the red disk. And those don't go away even when you start to pass the index 1 critical points. So intuitively, that's why we do see a disk in the complement of D prime, but we don't expect to see one in the complement of D. Okay. That's not a rigorous proof of why there's no disk. We'll get to that in a second. But any questions about the strategy? Okay. So how do you actually show that there's no disk? There's a couple ways to think about it. But basically, the approach that I'm going to outline here is if we do now look at the double branch covers, well, if this loop gamma, if it bounds a disk in the complement of the larger gray disk D, well, then when I take the double branch cover of the 4-ball over D, because that disk bounded by gamma doesn't hit the branch locus, it lifts to a disk bounded by the lifts of gamma upstairs. So I should get these nice disks in the double branch cover. And so what I want to do is look at the double branch cover and look for the lifts of gamma and ask, do those bound disks upstairs? And there's a couple different reasons why that's sort of morally easier. The one thing is that this thing is a complex curve, and so its branch covers emit these nice complex Stein structures, and so sort of they're nice spaces to analyze, whereas the complement of this is a little less obvious how it's going to shake out. There's various reasons, but one way or another, if we do look at this, when we take the double branch cover, we can explicitly write down what the 4-manifold is. And for one of the disks, we get the volume Kirby diagram, and this is sort of what's called like a Stein handle diagram for this 4-manifold. If you're not familiar with what that is, this is sort of a technical details for experts only slide anyway. But the point is we can explicitly write down a handle structure that helps us not only understand the 4-manifold, but sort of the complex structure on the double branch cover. And that curve, gamma, is going to lift to, one of its lifts is just going to be this curve which runs one time across a straight shot over the one handle. And it's easy enough to compute what's known as the Thurston-Benneken number of this curve, it's 0. And so you can attach a -1 framed 2 handle to the branched cover along this curve and get yet another Stein domain, because that's sort of 2 -1 framing. But if that curve was bounded a slice disk, then now you have a embedded 2-sphere of self-intersection -1 sitting in a Stein domain, which violates the adjunction inequality due to Liskett-Modich for Stein domains. So again, sort of breezing through that sort of as just for experts, but that's sort of the actual machinery underlying obstructing this knot from bounding a disk. And then there's one final bit of, technically all we just did is show that exact knot doesn't bound a disk in the complement of D. But we're trying to obstruct diffeomorphisms, not just sort of that knot. So the final thing you have to show is that if there was some diffeomorphism of the 4-ball carrying D prime onto D, you use a little bit of hyperbolic geometry to prove that, study sort of what can happen at the boundary, and you prove that any diffeomorphism that complements is going to fix that knot gamma up to isotopy. So you actually just need to study just that one curve and not its sort of translates under all possible unimaginable diffeomorphisms of the boundary. Okay, and so, okay, so that concludes the proof that these are smoothly exotic. And let me just see if there's, okay, yeah, so there's a couple of different things I could do with another minute or two, but do you guys usually run till 3:55? Should I stop now or till 4? What's the?
I think you could keep talking for another 5 minutes.
Timing? Cool, okay. So one quick comment, there's a different story you could take to think about the branch cover, which I'll just very briefly mention, which is that you could actually go back to the braided perspective, and the double branch cover of a braided surface in the 4-ball is going to give you a Lefschetz vibration. And so you can actually sort of translate the difference in the braided surfaces in the 4-ball into differences in the monodromy of the Lefschetz vibration in the branch cover, and you could study it that way. So the main thing to have here is just to show that the picture in mind that somehow you're going to get some different monodromies, and in fact, the difference in the monodromy of the Lefschetz vibration is just the difference in the braid factorizations downstairs taking the branch cover. Okay. But the real thing I wanted to get to is to sort of get through this slide is where did these surfaces come from? And so I'll just end with a quick cartoonish depiction of that story. So there's something known as the Cork theorem for 4 manifolds. There we go. Which basically localizes the existence of exotic smooth structures. Basically, it says if I have 2 simply connected smooth 4 manifolds that are closed, then I can find some contractible submanifold of 1 such that if I cut it out and reglue it differently, I get the other smooth structure. Okay? So, in fact, so you can think about Cork as some kind of knob or a gear that you can cut out and reglue in, so you can sort of turn it inside of your 4 manifold to change the smooth structure, but it doesn't change the topological structure. The reason that it doesn't change the topological structure is that, in fact, these submanifolds can be chosen to be contractible, and one of the sort of many amazing consequences of Friedman's work is that any subdiffomorphism of the boundary of a contractible 4 manifold extends to a homeomorphism. So if I cut something out and reglue it by a map which extends over the interior as a homeomorphism, I don't change the overall homeomorphism type. So the regluing extends in that case. Okay. So the most famous example is the Maser Cork, which we've drawn a hand-body diagram for in the bottom left. We've also drawn a Dane surgery diagram on the bottom right. And in this case, in the surgery diagram, you can really explicitly see this involution of the boundary 3 manifold, which you use to cut out and reglue. So that's just a quick mention of where these corks come from. The point is these sort of locally explain the difference in smooth structures on a 4 manifold. And this effort to sort of find exotically knotted surfaces in the 4-ball that I've been talking about, sort of this 0th step in trying to understand a version of Cork twists for surfaces. And so how does that work? So one way to cartoonishly describe it is to first note that if you have a smooth surface, disjoint from some cork, then when you sort of twist the cork, the surface lives on, but the ambient 4 manifold might change. So I might still have some smooth genus 2 surface that I can somehow identify with the one that came before, but its ambient space has changed. Okay, so sometimes I can change my 4 manifold without changing my surface in some sense. On the other hand, sometimes if I take a surface which does intersect my cork, if I cut out the cork and reglue it, there's no reason why that surface sort of glues back together again nicely. So, for example, oftentimes when you want to distinguish 2 4 manifolds that differ by a cork twist, you can look for some surface which does hit the cork and try to show that it disappears after the cork twist. So, for example, I could show that my 4 manifold maybe had a embedded 2-sphere in it originally, and then after I cork twisted, maybe I sort of tore up that embedded 2-sphere, and maybe I could distinguish my 4 manifolds by showing that there was no smooth two sphere after the Cork twist. Okay, so these are sort of two extremes of what could happen. But there's another possibility, which is that sometimes a surface can survive a Cork twist in a kind of a funky way. And the underlying point is that sometimes you do a Cork twist and it doesn't change your smooth manifold. So this can happen if you name your Cork Z, or sometimes N, depending on the font. And sometimes if a surface hits a Cork in just the right way, the 4 manifold might be unchanged by the Cork twist, but the embedding of the surface might be changed. I'll wrap up on this slide. Cartoonishly, we can imagine maybe we have some surface sigma, which intersects a Cork in just a delicate enough way that after you cut this thing out and reglue, the surface does survive. But maybe because of some asymmetric way in which the surface intersected the Cork, once you reglue it, it changes the embedding of the surface. And so morally speaking, that's what's going on in these examples I was constructing before. So they sort of originally arising from a handle calculus construction, sort of explicit with Corks, and then sort of reverse engineered the description in terms of braids, which indicates the different flavor of the construction. So I'll wrap it up there. Sorry for rushing at the end, but I'm happy to take any questions. So thank you, guys.
Thanks. Any questions?
Is there some sense in which you have a class of Braid factorization constructions which you can show are all actually, can you reverse engineer the other way? Can you find the Corks? If that makes any sense.
Yeah, it's a good question. I mean, so if one is trying, one of Salman Akbulut's preferred pastimes is to take known examples of exotic 4 manifolds and explicitly find some Cork in one. He's a very nice paper doing this for the Dolgachev surface and finding some explicit. It's not quite the Maser Cork, but it's another Cork. Sorry, it looks like my internet connection is rough. But a first thing to do would try to do is look at basic examples of surfaces coming from rim surgery and try to interpret those using some kind of Cork twist, surface Cork twist. That seems more doable at first than trying to sort of do a braid first approach. I think that as far as trying to do the braid first approach, what I would like to do is try to create something with, write a script to just play with braid factorizations. But I would probably do it by computer at least, because I don't know that. I'm not exactly sure what the guiding principle would be. I have some rough ideas, but a first step would probably be to try to generate some more examples by a computer search.
So this condition, I mean, the way you show they're not smoothly isotopic seems, well, you're saying that was not really ad hoc because that boundary gamma curve really related to your braid word as well, right? Is it?
Yeah, right. Okay, so that sorry?
No, go ahead. Go ahead.
Yeah, so right. I think that there should be, one of the things I'm trying to do now is there should be a cleaner way a more generalizable way to distinguish the smooth structures. For surfaces that come from rim surgery, there's so I think what Peter was hinting at, or it's related to what he was saying before, you can really understand the change of, for example, the Seiberg-Witten invariance on the double branch cover of two surfaces that differ by rim surgery. And so it would be nice to be able to produce some clean statement about what twisting with like one of these types of objects does to Seiberg-Witten invariant of some branch cover or something, do something more systematic. Yeah, at the moment, it's not quite clear how to make it less ad hoc. But right, like you said, ultimately, if one is willing to go hunting, oftentimes there's something, it appears, I think that it's reasonable to expect to be able to find something that tips you off to what the difference should be, like finding that that loop that you expect to differ in one versus the other because of the difference in the Braid factorization. In the meantime, I'll put up one of the other cartoons that didn't make it. Yeah. Another
will you give us a link to the full all cartoons file?
Sure. Sure. Yeah, I'll put the slides up on my homepage next to this talk. I'll put the link to the. So yeah.
Great.
Yeah.
Do you have a picture of the Cork in this, like in these two braids that you were talking about?
Okay, yeah, what's the best way to say, okay, so the, trying the best way to say what the picture looks like. So the idea, oh, thanks, Kyle. I'm trying to think of the best way to put it. So, see, Peter. I'm trying to think of the best way to articulate what it even means to sort of show what the cork is. But actually, in some sense, the cork itself is the four-ball. What happens is that you can show you can write down handle diagrams for the exterior of these two disks, and what you'll have is that two of the handles in the handle diagram will form a hop link. They'll just be unknots. Ultimately, they won't be cancelable. Normally, if we saw like a hop link with like a dotted one handle and a zero framed two handle in some handle diagram, normally we just cancel those. But if there's some other curves running over them, you can't cancel them necessarily. And so what the point is, basically, you take this this weird diagram of the four-ball that has some extra curve running through it that corresponds to your knot. And now if you switch which of those one and two handles, which plays the role of the one handle, which plays the role of the two handle, it sort of changes your identification of the four-ball, and it changes the way your knot sits in there. So I guess in some sense it's the closest I could say to like what the cork looks like. Actually, maybe I just yeah, let me try something real quick. The easiest thing I could do is probably just pull up the diagram itself, and then I think you'll see what I mean. So, so yes, what do I mean here? It's diagrams like this, where I'm gonna have some 3-component link, and 2 of the components, in this case, this black and this blue, if I forgot about this gray disk, then these actually form a hop link. It doesn't look like it immediately, but you actually could sort of pull everything off except for one. And so if I didn't have this disk, that would be a 4-ball. But with this disk sitting in there, it becomes sort of, I've sort of ruined the symmetry that would allow you to cancel them. But the thing is, I could actually reverse the roles of which is the dot and which is the 0. And so in some sense, the cork is kind of the 4-ball. It's not really, but yeah. So part of the problem is that it's not quite clear exactly yet what the ultimate correct statement will be for what it means to prove a cork theorem for surfaces, but it should be something about some subsurface that you can cut out and reglue. This is sort of the handle diagram interpretation.
Thanks.
Yeah. Sorry, it's not very satisfying.
No, that's good.
Yeah.
Other questions? Sorry. I think I have a problem.
I can't hear what you're saying, Akram, if you're saying something.
Yeah, now it's working. Should we thank you
Yeah,
in
that's fine.
35 minutes?
Sorry if the connection was a little rough, and
No,
my computer kept telling me that
There was no,
No,
I think
it
the
was
only thing that happened on our end was there were maybe some pauses that we didn't, I think that Zoom did a pretty good job of covering it up by just making it seem like you just paused for a little bit. I mean, all the words came through. There was no jointedness, just maybe they were delayed.
Yeah. Okay. Gotcha. Okay. Cool. Yeah. Good to know. Well, thank you, guys.
Oh, let me stop the recording
Oh, yeah.
and I'll talk off the record.